Welcome everyone for joining. Today we have Dave Raggett, who is the member of the WFSA European staff attached to European Research Consortium for Informatics and Mathematics. He has been involved in Web of Things and cognitive AI. So without further ado, Dave, the floor is yours.
Thank you. So thanks Hugh for giving me the floor for today. It's a shame that we couldn't be in person in Cardiff, but another time. And also it seems from the research themes on your website that there's a lot in common with what we've been trying to do in the Web of Things community group, about the idea of human-like AI, human-centered technologies, humans and robots. And I will try and show you some demos which explain that or justify that towards the end after presenting my slides. Oops. Focus, right? Okay, so I think I'd like to start at the beginning, as it were, after slushball Earth and the emergence of multicellular life and the emergence of neural networks, as it were. On the bottom right of the picture here, you can see a fossil for one of these creatures from over 520 million years ago. And so the emergence of neural networks, neural systems, enabled an explosion of life with predators and prey and all kinds of complicated behavior, sensors and so forth, all due to the warmer seas and high levels of oxygen. And then the brain has continuously evolved since then. And this is showing pictures of brains of mammals. And there's some common features like the cortex, which is the largest part, then the cerebellum, both of which are kind of convoluted, and then the brainstem. Anyway, they've evolved very dramatically, but there's very common features. So the way we think, in many ways, this must be similar to the way other animals or other mammals think. And this is a cross-sectional view, and the purple area is the kind of the stained of the neocortex, which is a thin layer on the outside. And you can see that the cortex is highly convoluted to maximize its area in a limited volume. And if you stretch the brain out, just kind of try a bit hard, but you can do it computationally, the human cortex is an area roughly 2,400 square centimeters. Unfortunately, it starts off large and it gets smaller as you get older, so mine is now probably a lot less than that, but never mind. Then if you look at the actual view of the brain in terms of its sort of components, we have the various cortical regions and the cerebellum and the brainstem at the bottom here. And so the different cortical regions play different roles. So essentially the cortex has it's a very thin layer of thin region of about 2 to 4 millimeters of 6 layers, and it varies slightly from one region to another. The visual cortex, or low-level visual processing, the parietal lobe for speech, pain, touch, and so forth. The frontal lobe for concentration, judgment, analysis, personality, problem-solving, language, etc. And then the temporal lobe, which is kind of interesting, it's like a hub and spoke, as I'll explain in a while. It sort of integrates information from other lobes, as well as doing high-level visual scene processing and semantic memories. Then we have the cerebellum, which is a kind of real-time motor control. So cognitive AI and the Sentient Web. Cognitive AI aims to mimic human memory, reasoning, and learning, inspired by advances in the cognitive sciences, and as I pointed out, the 500 million years of neural evolution. And the aim is to be able to mimic the brain at a functional level using conventional technology rather than having to explicitly use artificial networks, artificial neurons. And this will allow you then to place cognitive agents at the network edge or in the cloud and to have them communicate with each other. And there are many, many potential applications which we hope to explore in the community group. And I can define the sentient web then as a web of these interconnected cognitive agents featuring perception, cognition, and action. And this essentially subsumes both the IoT and the semantic web. And in terms of the terms, perception is sensors, dynamic access to information services. Cognition is data processing, reasoning, and learning. Actions, control of actuators, but also responding to queries, external queries. And then sentient in the sense of being self-aware in respect to the current state, goals, and actions. I steer clear of kind of defining what consciousness is. I think that's something we can leave to the future. And I also see the sentient web as the future for web search in terms of intelligent, collaborative, value-added services that know a lot more about you, but without giving that information away, as is currently the case with the web. So the long-term mission, this is kind of a vision, is to be able to enable cognitive agents that are knowledgeable, general purpose, collaborative, empathic, and trustworthy, that can apply metacognition, i.e. thinking about thinking, and past experience to reason about new situations, and support continuous learning based upon curiosity about the unexpected, is that how we do, and then have a level of self-awareness, as just pointed out, and but also to have an awareness of others, respect their beliefs, desires, and intents, in other words, to hold the theory of mind. And moreover, that these agents are multilingual, can interact with people using their own languages. So in some sense, this is a kind of a long-term mission or grand mission to abuse Star Trek to boldly explore the universe of the mind. And so a little bit more about the kind of what I mean by modeling the cortex here. So the idea of cortex, a database holding chunks, sort of a collections of properties with values as literals or references to other chunks, chunks of identifiers or names that are internal. And these chunks are associated with statistical information reflecting prior knowledge and past experience. And that, with these, analogous to the human brain, these databases have the potential to store vast amounts of information. And these databases can be placed locally or remotely and shared with multiple agents accessing them via access control policies. And one of the things that interested me when I was sort of looking into this was how it fits the web architecture really well for a remote invocation of kind of graph algorithms with a request response pair that sits very nicely on top of HTTP. I have a sort of attachment to HTTP, having launched the standards work on it back in the mid-90s. And so another thing is, rather than conventional databases where you just make a query and you get all the results back, like with Sparkle, for example, a triple store, web search like Google or Bing, you don't get that. You get the results which seem to be most important, most valuable to you in the current context. And so how do we model that? Because that's the way human memory works. And the idea is these databases are not only storing information, but they're supporting local algorithms which can be executed efficiently and scalable to handling big data. But beyond that, if you have the idea of federation of cognitive databases, you want to distribute algorithms efficiently across these databases, which may be remote from each other. And this is to mimic the operation of the anterior temporal lobe. Here I reference work by Sharon Thompson-Schill on the hub and spoke model for how the temporal lobe integrates information from different cortical regions. The picture of the lemon here illustrates the idea that part of your brain is sensing the shape, part of it's sensing the color. Then the other parts are thinking about what it would taste like, or what it would smell like, what it would feel like under your fingers. So all this information is being recalled. If you see a lemon, all this information becomes available, but it's stored in different parts of the brain, in different lobes. And it's also related to the Californian startup company, Numenta, and their 1,000 minds theory of intelligence involving non-hierarchical long-range connections across cortical regions, and their work on using field programming logic arrays for sparse networks. So the algorithms depend on the intended function of the database as basic storage and recall, like remembering things, but also specialized algorithms for natural language, spatial and temporal reasoning, and data analytics. So this is my diagram, which illustrates an architecture for cognitive AI. And it's essentially the cortex, which is acting like a blackboard, which the other systems kind of communicate through the cortex. So there's perception, emotion, cognition, and action. And I'll explain how these work in a sec. So first of all, perception. So we have many different senses. We have many different senses, but the essential idea is that the perception creates a short-lived representation in part of the cortex. But the cortex can also direct sensory processing as needed, as appropriate to the context. And then we have the, I'm not going to go to the details, but we have the different kinds of things like touch and pain, this homuncular model. Sound is different again, processing word by word. You can't process all the words at once. And then there's things like how do you detect prosody, attentional cues when somebody's speaking. And the eyes are very much more complex. Vision is complex because we have two eyes, which are kind of like multiple cameras in one. And then we have to swivel them around to things that matter. And they're very good at recognizing many different kinds of things, unlike deep learning systems, which can only really do one task, trained to do one task. And the cognitive context determines what's interesting and relevant. So that's the cognition or consciousness directing attention. And similarly, the visual system can signal to cognition things which are relevant, which are in the field of view and deemed relevant. And then we can pick this all up with reinforcement learning and implement it with techniques such as neuroevolution. There's a lot more work to do. I don't think we've only early in the path in computer vision, really. Then the architecture of cognition. So the idea here is this cortical basal ganglia circuit, and the kind of the machinery in the center of the brain, as it were. And so we have here the cortex on the outside, it's a series of modules, and communicating with our buffers to a kind of a rule engine implemented by the basal ganglia. And this combines, the idea of the chunks are combining the symbolic and statistical information. And the rule engine can then connect to many different parts of the cortex, rules representing reasoning, procedural knowledge, whereas the chunks representing declarative knowledge. And the experiments, the cognitive science experiments suggest that the execution of these rules is about 50 milliseconds, every 50 milliseconds or so. But the operations in the cortex take longer and are asynchronous. So graph algorithms are parallel, like we call it memories, whereas the rule engine is sequential. Kind of explains the sequentiality of consciousness. And it supports reasoning at many different kind of levels. And so, because again, summing up, we have chunks as a collection of properties that reference other chunks, include statistics representing reflecting prior knowledge of past experience. And in some ways, a chunk corresponds to an n-ry term in RDF, where you have that same subject and multiple objects. And we have modules, the different regions of the cortex accessed by buffers, which each hold a single chunk, and rules with conditions which act over chunk buffers and either update the buffers directly or invoke algorithms in the cortex, which then in turn update the buffers. And each buffer represents this current state of kind of the bundle of nerve fibers connecting to a particular cortical region. And these buffers also can be likened to HTTP clients, with the cortex can be likened to sort of HTTP servers. And this, I'm very much indebted to John Anderson's work at CMU on ACTA over many decades. And this model you can also liken it to the REIT algorithm by Charles Forgy, in that if you want to scale up the rule engines, you have to find some way of dealing with the fact if there's too many, if they're operating over too large a database, or there are too many rules, and the performance runs like a snail. And so the brain, even neural evolution, has very kindly sidestepped that with this architecture. Actions, this is the corticocerebellar circuit. So the idea is cognition devolves actions to this system, which supports real-time control of parallel processing. And it's interesting to note that in the brain, in the human brain, the cerebellum, although it's kind of a lot smaller than the cortex, it has actually 3 times the number of the nerves in the cortex. And it acts like a flight controller, managing the operation of myriad muscles in real time, coordinated with perceptual information it receives from the cortex. So it's offloading processing. So I can ride a bicycle while talking or thinking. The performance degrades, obviously, if you look away when you're driving, if you're, so long as you're looking roughly in the road, you might be looking to road signs, but as long as the corner of an eye, you can see the lane ahead, you can continue to lane track, but directly further away than that, lane tracking goes to pot because you're using dead reckoning. And then there's this idea of monitoring and signaling back to the cognition when high level control is needed, when you have to replan movements, for example. And the idea is learning for experience, which I'll come back to in a while. And the implementation is a sort of suite of real-time continuous state machines. And I think there's a lot of advantages for applying neural ordinary differential equations from the work by Chen et al. From a couple of years ago. And examples of talking, walking, cycling, playing the piano. And then we have the idea of emotions and stuff, where we're much less advanced, although we have reasonable theories about emotions. We have yet to try to integrate them with our cognition systems. And so the idea is very important from an evolutionary perspective, avoidance of harm, predators, prey, courtship, care of young. And it's enhanced for those species like our own, which live in social groups. And so you need emotional intelligence is about being aware of what others are feeling, but equally signaling your own feelings effectively. And then emotions, it's about a feeling and something it applies to, with a kind of whether it's positive, neutral, strength, the valence, or the level of arousal that's calming, exciting. And moods is a kind of long-lasting emotions. And then you can think a bit more functionally in terms of what triggers emotions and what effects they have. So it's triggered by the perception in terms of like seeing a predator or seeing a lion or a wolf, reasoning about situations, recall of emotive memories, so socially for planning and recall, and implemented as functionally in terms of classification networks. And then the effects of emotions on instinctive behaviors like fleeing from danger, but how these are controlled cognitively. And then prioritizing what you're thinking about and what feels important. Marvin Minsky's Emotion Machine book goes into this in some detail. And then there's the influences on how what memories recall, or new memories, reinforcement of existing memories and behaviors. And then there's Daniel Kahneman's sort of a idea of fast, instinctive versus slow and deliberate. And so the idea being that we can't always take a deliberative, analytical approach to situations. We need to be able to react quickly. And so the kind of a fast, instinctive appraisal and response, avoiding that kind of delay, but equally subject to errors. So it's a trade-off. And there are many ways to think. So currently a lot of, like in semantic web and logic, focuses on deductive reasoning. There are many other forms of reasoning that we'd like to be able to handle. So for example, build induction for building models to explain irregularities in kind of a noise environment, abduction determining what was the most likely cause of something, reasoning about how you achieve goals, causal reasoning, and then fuzzy reasoning involving blends of states, and then they've got different kinds of critical thinking, as you see in the box here. And then we want to mimic human memory, so we only want to recall what's relevant to the current situation. We have various things, psychological facts, as it were, interference, new memories, they block older memories, our ability to recall information drops off unless we practice it. There's the kind of spacing effect with closely spaced repetitions of less effect. And we have spreading activation of priming effects. And then there's the, if two facts are kind of equal in strength, roughly equal, then they're equally likely to be recalled. And so it's the role of Gaussian noise to support that. And then different ways of implementing such systems, obviously like ACTA, and my own implementation is based on chunk graphs. Then Kelly's done this approach based on sort of vector spaces and holographic memory. And Chris Elias-Smith at University of Waterloo, he's got this extensive work on pulse neural network implementations and what he calls semantic pointers. And on the right side, we see kind of an idea of a learning curve, which is the left part is kind of as you're learning, and each practice boosts the signal, boosts the kind of strength of that piece of infinite knowledge. And then if you don't use it, you'll lose it. But if you keep practicing it, it boosts the strength and you are able to keep it long term. And we can say that the spreading activation thing, nature figured out the PageRank algorithm many millions of years before Google. So machine learning, that unfortunately, that good old-fashioned AI assumed manual development of knowledge, which doesn't scale. So we need to figure out how to use machine learning for declarative and procedural knowledge, where there's a lot of work there to build upon. The idea of semi-supervised learning, i.e. human-machine collaboration, and as a human-guided exploration. So you're essentially not trying to do something directly, develop something directly, but you're working with an agent as a kind of a intelligence amplifier, perhaps, where you are able to help guide salience and things to do for that agent to explore. Then there's learning at multiple levels of abstraction, and an example of hierarchical reinforcement learning is a case in mind. Then there's this idea of active learning or continuous surprise-driven learning. And I'm trying to remember who said this now. Somebody pointed out the idea of humans as prediction machines, that we attend to novelty to improve our predictions. So we're always trying to explain what's going on in the background. And when something doesn't quite go as expected, that's brought to our attention, our consciousness. Then there's the different ways in which you could train cognitive agents. One is by learning through experience of real or simulated environments, and having different agents interact with each other, but also with people. So that's kind of like the idea of learning in the playground. And the other is the idea of using natural language in particular to teach agents skills, and like in a cognitive classroom. And the diagram on the right illustrates different kinds of learning with procedural knowledge, using reinforcement learning, and then different kinds of supervised, semi-supervised, unsupervised learning. One of the things what makes us human is our mimicry of each other. So babies, like on the picture on the left, learning to smile from interacting with their mothers. Children copying speech sounds, copying regional accents, picking them up really quickly. Then there's learning to say, to speak, using language more richly by listening to others. And then there's, a bit old maybe, imitating the dance movement of others on the dance floor of the TV, your favorite band. And if you're really skilled as a musician, you can play a piece of music after listening to it. Then, of course, fashion, copying the same clothes as your friends. So these are all emotionally satisfying, generate a sense of belonging. So what is the functional architecture to support social mimicry? And so essentially, it's about an internal model, a hidden model, as it were, has to be learned from the lower level sensory data by increasing levels of abstraction, but involving multiple modalities. Like, for example, the baby has to use speak, vision, and touch and sounds. And then you have to learn to map this back down to a low-level model for motor control, decreasing levels of abstraction for the cerebellum. So this is the, in other words, the perception and action are very different systems, but they're designed to support this kind of mimicry. And we have also the statistics of recognition of patterns being shared with the generation, essentially to high level. And for example, for natural language, and incremental learning, which is involving very weak supervision, involving effective models, more like an evolutionary context from many potential alternatives. And so that brings us back to sort of things like nature versus nurture. So what's inborn, what you have to build into an agent, and what can it learn once it's got started? And so we have this idea of how much and what kinds of knowledge are needed to bootstrap learning, and with a man-made artifacts. Obviously we can do manually programmed facts, rules, graph algorithms, and so on. And then we have this idea from psychology, the 3 stages of learning, forgetting, progressing from declarative to procedural, as shown in the picture on the top right. Chunks is the basis of facts and rules, and heuristics and metacognition to speed the process. And already mentioned Minsky's ideas of the emotional as being cognitive regulation. Then there's the idea of recall, the idea of remember similar situations is very important. So it's using analogy and metaphors. And as we have the work by Simon in '92 on intuitive decision making is nothing more, nothing less than recognition. And then even earlier, Klein, there was some work reported that fire marshals tended to make rapid decisions by generating a single alternative, mentally simulating its outcome, and either making minor revisions or adapting the nearest closest alternative. So we think in terms of possibilities, not in terms of logical statistics. And then we have this diagram on the right, illustrating sort of top-down cognitive regulation, and then bottom-up kind of instinctive and emotional influences. So I'm going to spend a little time explaining chunks, and then go into the demos, and then go into questions and answers. So chunks is a term from psychology, and I've kind of picked it up, I guess, and used it to define a kind of a language for facts and rules, and defining it as a simple amalgam of RDF and property graphs in the spirit of the idea of making the RDF easier and more general. And so chunks correspond to concurrent firing patterns across bundles of nerves to particular regions. And for this, I recommend you take a look at Chris Elias-Smith's work on semantic pointers. So each chunk is a typed name collection of properties and names or literals. And in the image definition, we've got numbers, booleans, dates, string literals, and comma separated lists. But the exact type of literals is something that's up in the air. There's a simple means to map between chunks and RDF, and mapping names to the RDF URIs, and also a short form syntax for chunks which denote single triples. But there's also the idea of a minimalistic version of chunks, because I think in the from the neuroscience perspective, it's unlikely they embody directly the literals. It's more likely they just involve references to other chunks, and you can use sort of dictionaries at the edge or lexicons which map them to these constants. So if you wanted to represent numbers, if you think about how we learn to do some ordinary calculations of numbers, you think of it in terms of numbers 1, 2, 3. And you think about the tens, the units, and so forth. So here's some examples on the right of a chunk, and the idea of being able to have fewer simpler syntax than for JSON LD. And you can either use new lines or semicolons for separated. And the actual chunk ID, when you manually author the stuff, is optional. If missing, it's automatically assigned when you add a chunk to a graph. And if the chunk already has, this graph already has this chunk with the ID, it'll be replaced by this one, and so forth. The idea of a type here, like a dog, is it's informal. It can be used for loose grouping, but it may imply an ontological constraint. So moving away from formal logic, and I'll get back to that later. So there's the idea about if you want to have more complicated stuff, which is like analogous to named graphs, for beliefs, stories, supported speech, kind of the examples in a particular lesson in the classroom, abductive reasoning, search query patterns, and things like that. They involve statements about statements. And so how do you express those in chunks? And I picked an example from John Sower. Tom believes that Mary wants to marry a sailor, or in other words, that Tom believes the proposition that Mary wants the situation in which she's married to someone who is a sailor by profession. And then we have the idea on the left there, represented as chunks, using at context to name a particular context. And contexts are also useful for episodic memory when you want to describe facts which are just true in a particular situation. An example, when you visited a restaurant for lunch, you can talk about what you ate at that or drank at that particular lunchtime. You maybe sat by the window, you had soup, followed by risotto, and then you can ideas, having got these named contexts, you can express a sequence of episodes as a relationship between contexts and use that for inductive learning. We have the idea of chunk rules expressed in terms of chunks. So the idea of condition action rules, and this again is borrowed or adapted from Actor, except expressed in a more convenient syntax. Anderson's work started many decades ago, and he was based his work essentially around Lisp, and now we're a bit further on from that. So the idea is you, when you update one of these module buffers from the earlier diagram, that triggers the rule engine to find and execute the best matching rule. And you see the selection of matching rules, and then it uses stochastic selection of which rule to execute based on the expected utility according to past experience. And that's again the work that Anderson and his colleagues have pioneered. And the conditions match the content of the module buffers. The actions update the buffers directly or invoke module operations, for example, in calling a fact from memory, asserting a fact to memory, invoking an external operation. So in the demos, we have things such as the moving a robot arm, turning on a light, turning on a radiator, or speaking, like saying hello. Variables are used to pass information from conditions to actions. And then we have a means to name the module, defaulting to a module called goal. And then there's this variety of different operations you can invoke with @do. There's the built-in operations where I've used the names from HTTP because the analogy with HTTP. And also the applications can define the module operations, and that's the way in which things like the robot is controlled. On the right, there's an example. I won't go into details now, but this is an example through counting and count up 1, 2, 3, or 5, 6, 7. And it involves essentially 3 rules. One is to initiate the process. The next one is to incrementally move up by 1 digit. And the last one is when do you stop counting. So I have a demo on autonomous vehicles. This is one of my earlier demos, which is way too ambitious. And so I did a lot of work on spatial indexing and trigonometry and stuff. And the idea is to take data exported from OpenStreetMaps as XML, transform that by a script into chunks, which are much smaller. And the idea of you have points of latitude and longitude, paths, a sequence of points, and roads, a collection of paths. And I happen to pick my own local town in Frome in Somerset. And then the idea of using graph algorithms for spatial indexing, the quadtree index, using chunks itself, and then using an A-star algorithm as a graph algorithm for route planning. And then the idea is you have, there's lane tracking, and then it has visual models alerts when you're approaching a junction, when you're entering or leaving a junction, when you're reaching a destination. And then there's other stuff to do with indicators, braking, and so forth. So I don't go into details on this, merely I'll show you, it'd be better if I can figure where I've got it. It's that one. Oh, the sandbox. Maybe, yeah, I'll come back to the sandbox after this one. So go away. So this is the streets in my hometown, and we can, I don't know if this will work. And you can see lane tracking going on and so on. All right, so that's lane tracking. The red blob in front of the car was kind of where the driver is essentially looking, and that's sort of a algorithm based upon how we think people steer. And then there's various other things corresponding to the nodes in the network itself and the information about them. And then we've got information at the bottom corresponding to the speed, the steering, of the column angle, and the current road and where the next stop will be. In this case, it's already starting the move. And so if I come back to here briefly, what are we doing? So the idea then is to integrate rules, which I haven't quite done because I switched to other demos at that point, but I need to come back to this. And the idea is when you're approaching a turn, then that will trigger a rule, which is this is what this alert is, a kind of a goal, which is set into a buffer, and that then triggers this rule, which then it recalls information about the upcoming turn from memory. And when you get that then triggers the car to stop braking, using the information about this turn to start signaling. And then when you get to the turn itself, that point, it's you use a start turn, goal has been asserted, and then we start to steer. We switch from lane tracking to steering between one lane to the other. And then we start, because we stopped at the junction, we'd have to speed up to 20 miles an hour. I thought, be cautious. And then, carries on from there. Now, I'll go back to this. What I forgot to show you was we have this chunks rules. We have this informal description of the chunks and rules language on GitHub, and it goes into a lot more detail. And then my colleague Francois Daust in the W3C team has been helping with developing this into a formal specification for a community group, which I'll come back to later. I've also created a sandbox, which allows you to try out or even experiment with chunks and rules in your web browser, and even to save them to your local storage to the browser for a subsequent session. And the idea is to expand this, so we've got this counting demo, to extend this to a wider sort of things. So let's see if we start. So hang on, we need to recall it. Anyway, I'm forgetting how my demo works. Oh, I know, step, that's why. You have to press start. In this one, you just press start, then you have to step. Okay, so now we're going from 2, 3, and we can see below, we can see the buffers, we can see the rule that's just been applied, we can see the variable bindings at this point, and we can see a log of what's been going on. And then the idea is to move this into a wider demo. And then we have a test suite and in support of the specification. And let's see if I can run the tests. So it's basically a lot. I'll show you the rule set, perhaps, if it has it in this one. And you can see it stepping through. And you can see also the log as it's applying different rules. And then we have a kind of a facts graph it's using, it's not a huge one, but like in this case, a knowledge about which towns, UK towns, and which county. And then there's some rules which are used for each test. I'm going back to the slides quickly. We have a smart home demo. This is being developed with for the Alliance for Internet of Things Innovation. They have like a task force working on semantic interoperability. And so we're working there. So I wrote this demo first of all, and now we're trying to explain how this relates to the different kind of ontologies you'd use for this. And so if we look at the ideas, we have a room, we have people in the room, we can change the number of people in the room through the user interface. We have a radiator, a thermometer, which shows you what the temperature of the room is and what the the thermostat setting is. We have a window which shows you kind of whether it's light or dark outside, what time of day it is, which you can change through these radio buttons, and also the external temperature. And so the idea here is a dynamic simulation of the kind of thermal model of heat flows into and out of the room, the manual or automatic control of lighting and heating, the forms interface for controlling the who's in the room and the time of day. And there's a mix of declarative and procedural knowledge and default reasoning. And so where's the, oh, here. So, all right, okay. So first of all, you can see that just John is in the room, and you can see it's 12 degrees outside, and he likes a temperature of 18, and so the temperature pops up and down around that point. If I can add Janet into the room, and so far so good. The lights are turned off because it's daytime and it's bright enough. If you go to the evening, now we see that Janet likes warm lighting, so we've got warm light, but John, he prefers cool lighting, but Janet takes precedent for that. But John takes precedence when it comes to temperature, so he prefers a cooler room, so he dictates what the thermostat setting should be there. And if we take John out of the picture, we can see that now the target temperature has gone up. And we can see, it's going up and down. And if we get to night, we can see that the radiator now is struggling to warm the room up because it's quite cold outside. And then we can see the log of the before, and we can see some factual knowledge about the preferences and the precedence between the two people. And we can see a whole bunch of rules to do with the default reasoning process using the chunks. And so that's that one. And then we have a factory demo. So this is developed for a summer school on AI for Industry 4.0, and also as part of my a project called Boost 4.0, which is big data for factories, which we just had our meeting this week, but online, of course. And so the idea is to have a robot in a bottling plant. So we have a conveyor belt which brings empty bottles, and you want to pack full bottles into boxes, 6 at a time, on a conveyor belt to shipping. And so I'll explain. I think I'll show you the demo and then I'm back to the explanation. All right, we've got it. Yeah, okay. Fingers crossed. It's got sound effects as well. So this is all using HTML, the context 2D, and the real-time, high-precision real-time clock available to JavaScript programs. So the conveyor belt brings empty bottles, and then we fill them, and then we cap them and pack them, in which case I'll stop because it gets too boring. So here, if we look at how it works, oops, we have, what's going on? So it's a live simulation of the bottling plant. It's real-time controlled by the cognitive agent, which is controlling all the 2 conveyor belts, the robot arm, and the filling and capping station in real time. And so we have, so essentially cognition is used for the control, and then if that's the cortico basal ganglia circuit, and the cortico cerebellar circuits using for the real-time control. And so in this case, this first rule, we're adding a bottle when belt 1, this is the first belt here, has space, and then adds a bottle when it's the space at the beginning of the belt, and then it goes on to request that event in the future when the next time there's more space. So the idea here is to you're waiting for something to happen. It might happen in the future, it might have already happened, but then you want to do something. And so then we have like stopping the belt, in this case, when the belt is full, and then moving the robot arm and it is ready to grab the bottle. Then here we go, step 1, then step 1, the robot moves into position closer, and then it's able to grab the bottle, and then pick it and move the bottle to the filling station. And the slide on robot control. So we have perception, where the state models are updated in declarative memory, the cortical modules. Events model as goals, which trigger rules, and a goal queue to avoid missing closely spaced events, and when things happen too much at the same time. And then actions is a concurrent asynchronous execution of actions, analogous to HTTP, and the delegation of the execution, the real-time execution, to the cerebellar circuit, leaving the rule engine free to keep thinking and responding to other things. And then the idea of the cerebellar stuff being modeled as functions of time using a high precision timer, and the robot itself has 3 rotational joints and a gripper, all smoothly accelerated and decelerated according to their individual capabilities. And in a sense, this is threaded control of continuations. And it's about this idea of doing something when something has happened, may already happened, waiting for a robot motion to complete, waiting for space to free up at a conveyor belt, or the belt to get full, waiting for the bottle to be filled or it to be capped. There's the possibility of integration of existing robots through network API using cognitive AI for high-level control. And then there's further possibility of using a lightweight ontology for validation of rules, for planning and replanning and meta-level reasoning. And then for richer interaction with robots through natural language and emotional intelligence. And very quickly, because I'm aware of the time, if I can show you the facts graph, which illustrates the kind of ontology. This isn't actually used in this particular demo because I ran out of time. But the idea here is how to express an ontology in chunks. And so we have different kinds of a bottle with properties. We have the types for the properties. And we have a robot in terms of its arm and various things, how you control it. So you're telling where you want the robot arm gripper to be. You're not telling, cognition doesn't tell what all the joints should be. It just tells what it wants is goal driven. And then we have the belts and so on and so forth. So come back to this, where we got to, Whiskins away. My cat seals, it's food time, it's not. So there's a bunch of other demos. There's some earlier ones. There's a counting one showed you, which is ported from Actor. There's a decision tree, like when is it suitable for the president to go golfing? There's a test suite and the sandbox, which I showed you. And there's an ongoing work on natural language, which I'll finish up on before the questions. So natural language, essentially, if you focus on it as social communication, and for teaching, also for teaching skills, this classroom idea. And the idea is you want to be able to have a cognitively plausible model for natural language, but both for understanding and generation, inspired by the work in the field of cognitive linguistics. And so the idea is to use incremental word-by-word processing, concurrent syntactic and semantic processing with no backtracking. And the idea is to reduce the load, unlimited working memory, and to use statistical information to guide choices, so that priming, semantic priming from the words you've already seen or recently. But it's the idea being able to offload cognition through graph algorithms, and then to escape the kind of constraints of that sequential processing model. Parsing uses robust shift-reduced parsing with a small set of rules, which the grammar is essentially implicit in a small set of rules. And it's a small set of word classes of parts of speech. They're sort of similar to the ones you see, very similar to the ones you see in dictionaries. And then you can see an example below of how a particular phrase is broken up into a dependency tree and then into a set of chunks. So chunks represent sort of a variety of properties. So we have, for example, if we look at, I don't know, the verb phrase, we have the verb is want, subject is chunk 2, and we have chunk 2 is the pronoun I, and so on. The idea then, these parts of speech allow utterances to be segmented. The segments can be arranged in a properly nested spanning tree, as you saw on the left, bottom left. But the choice of attachment depends on syntactic and semantic considerations, which needs to be processed concurrently to avoid the backtracking. And semantic agreement overrides adjacency for this attachment. And you consider this phrase structure, the incremental growth of the phrase structure as a data stream for understanding meaning. And the mapping rules is the work which I'm sort of currently involved in. Is the idea is to map between the syntax and semantics, and to learn these over time. And so I've done some existing experiments. So very quickly with the demo again. Let's see. Yeah. Okay. So this is my first experiment. So it's got a simple shift-reduce parser, and then if we either type the command in, or taking, let's see if I can get it to work. Move the green disk to the middle peg. Not quite. Let's try once more. I need to be more American in my move. Move the green disk to the middle peg. I'm not sure why I've done wrong now. That should work. Normally does. Oh well. Then we have another demo, which is the idea here is we have looking at dinner, restaurant meals as a well understood environment of the Shank and its work and others. And so the idea is that you want to model two agents. So in this demo, it actually creates two agents, one agent representing the customer and the other agent representing the waiter. And if I run the demo.
Good evening.
Good evening and welcome.
A table for one, please.
A table for one.
Okay, let's
certainly just here.
Stop there for a moment. So the idea here is this is actually two agents communicating with each other. In this particular demo, it's passing chunks, from exchanging chunks, and the work I'm doing at the moment on mapping syntax to semantics is involved. That work will then allow me to exchange the language itself. So what was that? Yeah, okay. So it's ongoing work on the on these mapping rules, and the idea of the future being able to learn continuous learning about learning mapping rules by generalizing from rules you've already seen or inferring rules as a way of explanation, and then the meanings on previous unseen rules. So we have a cognitive AI community group, which is we very much welcome new members, and the focus of developing, demonstrating the potential of cognitive AI. And the idea is to do a combination of open source implementations, scaling experiments, and outreach. And there are many different possible areas. I haven't got time to go into details there. I'll get back to that in a moment. And then I was briefly wanted to finish on the relationship to other approaches to AI. So deep learning is inspired by models of neurons, of backpropagation, very successful but increasingly obvious limitations. And whereas the semantic web is founded in this Aristotelian tradition of logic, formal semantics, and model theory, and essentially what's provably true given your assumptions, inference rules, but it's intolerant of inconsistencies. Whereas cognitive science is more broadly the experimental study of the organizing principles of the mind. And so cognitive AI is taking this broader perspective of mimicking memory, reasoning, and learning, inspired by the work advances in the cognitive sciences. And basically what's useful based on prior knowledge and past experience. And then we have these guys, Aristotle, of course, did a lot of early work very broadly, Newell, who worked particularly on production rules, Anderson on combining production rules of graphs, Minsky on a whole bunch of stuff, frames, which are analogous to chunks, but also in the motions, and Johnson Laird, to get this quote at the bottom, humans don't rely on the laws of probability, logic and probability, but rather by thinking about what's possible. So I have this slide here, but I'll just briefly come back to the, so we have the cognitive AI group. Okay, why is that not there? Reload this page. Typical. The hope the web hasn't gone too slow. Well, I'll leave that for a moment. Then we have also a GitHub page, the community group, which kind of explains things and also has some links, including the slides for this particular talk today. And it also has a link to the frequently asked questions. We have how do you, some advice for contributors, about different kinds of roles you could play. We have frequently asked questions. So the questions I've got from this talk and previous talks, I've tried to compile into things there, so we can always come back to that. And so at that point, I would like to open the floor for questions.
Thanks a lot, Dave. Anyone has any questions? I think we have about 10 minutes for questions.
I've got a question. Can I ask you a question? Yeah.
Yes, please go ahead.
Yeah, okay. Thank you very much for your interesting talk. It's really interesting topic. I just wanted to know about the unique feature that the chunk architecture has that I that can't be found in other architecture, because the functionality and
I guess there's one way is how does it relate to other approaches to AI, and the other question will be how it relates to RDF and property graphs. So I guess let's do the second one first. So RDF allows you to define graphs, in terms of triples, whereas property graphs are forms from nodes, links, and properties, and chunks can link to other chunks by properties. So, but you're also free to express the links as separate chunks as a representational choice, and that's kind of relates to the connection between property graphs and RDF. Sometimes you want to annotate links, which is the key advantage of property graphs, but it also requires reification in RDF. And so it's handled sort of very naturally in chunks. And then it's also this the idea and advantage of RDF using URIs is kind of makes it easier to help with interoperability, and hence there's a relationship mapping to that. But I think I should have started with this one first. I realized that good old-fashioned AI and expert systems, semantic web based on symbolic representations but not statistics, deep learning embodies statistics but not symbols, although statistics can act as a weak surrogate for semantics. Cognitive AI combines symbols and statistics, explicit representation of semantics, and then seeking expression of the cognitive sciences. Like deep learning, this takes some stuff from the cognitive sciences from quite a long while back, and everybody now recognizes they need to look at more recent advances in the cognitive sciences for advances in artificial neural networks. But we don't have to directly model the neural networks. We can also run things perhaps on everyday hardware just as efficiently. We just have to look at the functional or computational model. And so there's the, anyway, so there's further explanations there. So the different approaches to AI are largely complementary. So deep learning is good for processing raw sensory data, whereas symbolic AI is good for agreements and interoperability, where communities need standards for conducting business. But in the long run, the boundaries of different approaches are likely to blur. For example, new generation deep learning, which more closely mimics perception. And the blending of similar statistics is needed for machine learning and for more powerful, more general forms of reasoning.
All right, thanks.
Yeah, Rosie, go ahead.
Okay, thank you very much for this interesting talk. Dave, really inspirational talk. I want to ask how big the cognitive AI community is, and what do you think about terms like human-like AI or contextual reasoning? There appear different committees use different terminology. So is cognitive AI equivalent to human-like AI? So there are technical committees, IEEE technical committees on human-like AI.
So that's a good question. I'm not really in touch with the IEEE community, but one of the members of the cognitive AI community group is introducing, we're arranging to liaise better with them. From what I understand, their work is more higher level, whereas here the idea is doing more at the engineering level. So I think that should be complementary. And there's another group in the W3C, the Artificial Intelligent Cognitive Representations, or AIKR community group, which is again more looking like a survey across things and looking at ethical and other kind of surveys, but not actually looking at the engineering of AI. So this group is still very small, but the work obviously on the cognitive science is very, very large. So it's building upon a very large body of work, and equally like cognitive linguistics is a very large field. So there's essentially lots of people working on different aspects of this, but we now have to try and bring this together. And I think there are lots of opportunities.
Absolutely. Yes, I really like your approach. I wasn't familiar with chunks, to be honest.
Well, it's new, so that's why. It's new in one sense, but it's essentially that Anderson has chunks in his actor model. That's been around for many, many decades. But his interest is in his particular the research questions for his particular field, he wasn't interested in how you can apply this outside his field. So I think now we need more interdisciplinary work where we can take the ideas from these different fields and bring them together. And that's really hard because everybody uses their own language and argot. So to try and understand it, it's kind of very uphill, but nonetheless necessary.
Yes. So if we wanted to work on a new problem, for example, curiosity, okay, so we need to look at the literature, I guess, identify what triggers it, what effects to expect, similar to your approach you showed. But some of these cognitive processes are not very well understood by psychologists, even.
Right.
So what should we, as engineer, do if we want to develop robot curiosity, for example, or imagination, artificial imagination? So how to overcome that barrier? For me, it's a barrier.
So I think there that we can expect further advances to come from the cognitive sciences over time, but equally we can build tools which illustrate some of the ideas that will help them to think, like the idea of computational AI, computational models have been really helpful in the cognitive sciences. So I think the basic idea about curiosity, I think it's this idea of the mind as a prediction machine. That's when something doesn't quite match your predictions, this is a kind of in the background process, then you that raises attention, and then you look at that and you try to find an explanation for that. Obviously in balance of everything else that's going on at the same time. But that's something you can definitely see in young children and so on. And so we can build models around that. Then there's the questions of what does it mean to build a prediction machine? And how do you identify things which are unusual anomalies? And then how do you learn from that? How do you seek explanations? So that can break down into a number of different challenges. And the real issue here then is to find some really good examples to build a demo around, or build something around, like some data sets or some test cases. And similarly, there's the thing about trying to understand causality rather than just correlation. But if you think about, you can make correlations between the inputs and the outputs, as it were. But to understand in terms of causal terms, you need to be able to manipulate it. So how can you do that? So can you do that through virtual environments? So you can simulate learning in the virtual environment, or even in a real environment with a robot, but that's obviously more expensive. So I think that the challenge is to identify interesting scenarios, test cases, which you can actually make progress. But I think we know enough. We can break these things down from an engineering point of view and find solutions. And then we can feed that back to the cognitive science areas.
Thank you very much. This gives us a lot of encouragement, I have to say, your reply and your talk in general. Thank you.
Well, one thing, at the moment, the demos I showed were using a kind of a JavaScript library. But over the next couple of years, I want to be able to scale up the performance considerably. So that means essentially implementing this discrimination network for the REAT algorithm, essentially. And then looking at ways to make to scale up to very much larger sets of facts and sets of rules in high performance, and the potential for doing that, acceleration. How can that integrate the work that W3C has been doing about integrating with the AI and graphics accelerators? And there's sort of work going on at the moment. Can I ask you questions back? Do you guys, are you doing much work on natural language, for example?
Yeah, a little bit on semantics, yes.
Okay. Because here the idea that with this idea of pipelines, where is it explained somewhere? Oops. Yeah. So the idea of the cognitive AI modeling language in terms of a series of layers. So one layer with the words, next layer with a syntactic phrase structure, like I showed you, and the further layer with the semantic and pragmatic representation in terms of chunks. So each of these layers can be expressed with chunks. So the process of natural language with understanding and generation becomes a mapping between the chunks and the statistical selection of rules as appropriate. And then the further layers dealing with phonology, prosody, morphology, and so on. And then the challenge, always natural language being highly ambiguous, and how can you deal with that ambiguity in a limited constrained memory? And traditional computational linguistics are used probabilistic search techniques, where they used essentially statistics in lieu of semantics, on lieu of statistics about semantics, which is kind of odd, really. It's like we need to talk to each other rather than just ignoring each other's fields. And so there's, and I kind of like Christopher Manning's slides at Stanford University on statistical parsing. Then there's the work like BERT, which is the idea of transform models for looking across words, long-range correlations, but their kind of approach is not linguistic, not cognitively plausible because they need to analyze all the words at the same time. Which, you know, so it's an interesting approach, but they also don't handle semantics except very indirectly. So they're kind of limited to what you can do. You can't do a lot of interesting reasoning tasks with BERT. And so the idea, and the other thing is to note that children are very effortlessly pick up language despite the amazing complexity of languages. So that's telling us a great deal. We just need to listen. So I think there's, I'm looking particularly next year to seeing how far we can get with this.
Thank you. Thank you.
Thank you very much, Dave. I think we reached end of the time allocated. If anyone have any questions, I think they will be more than happy to answer questions over the email. So thank you very much, Dave. Thank you, everyone. Have a good evening.